Welcome back to your physical science class. I'm hoping that all of you are doing well and there's no issues with anyone. Hopefully you all have already submitted your homework assignment for today about the materials we had from the last chapter. We're going to continue on with the next chapter talking about chemical bonds. Now the core concept for this one is the electron structure will explain how and why atoms join together in certain numbers. The last class what we talked about was the electronic structure and how those electrons are arranged for all of the different elements that we have. So as a review, we have the atom as the smallest elemental unit. And then we build upon that with this molecule. That's the smallest particle still retain the characteristics of chemical properties of a substance. And they can be diatomic, triatomic, or monatomic. In other words, monatomic is one atom alone. An example of that would be all of the different noble gases. Because remember, they are satisfied that they're with their octet of 8 electrons out there. So helium is the sole exception where it's satisfied with just 2. So helium is monatomic, neon, krypton, all of those are monatomic molecules. Then you have diatomic ones, where you have 2 oxygens bonded together, 2 hydrogens bonded together, 2 chlorines bonded together, 2 nitrogens, etc. So those are all diatomic molecules, 2 atoms, 1 molecule. And then you have those that are triatomic. And this is the same element, but there's 3 of them together. And the example is given in figure 3 right here, which is ozone, O3. Okay? That's the smell that you get in the air after a lightning strike. That is the ozone. Now, chemical reactions involve the formation or breaking of chemical bonds to form new materials. In this case, water reacts with carbon dioxide when you have heat to grow a plant plus oxygen. Okay, there's actually the green plant is kind of simplistic because it forms through photosynthesis. It's going to be forming dextrose or some other sugars as well. Likewise, the plant material, when you burn that, when oxygen gives off water, of course the energy, and carbon dioxide. So the chemical energy is the internal bonding energy that is given. A chemical equation is the symbolic summary of a chemical reaction. These are rather simplistic ones here. We'll continue on and they'll get more appropriate for these. Now, going back to what we learned in the prior chapter, the outer electrons are the determining factor for the chemical properties of an atom. And a rule is the octet rule. Atoms attempt to acquire an outer shell of 8 electrons. Electrons can be gained, lost, or shared in that process. Sodium, for example, right here. As you can see, the first energy, it has the 2 electrons. Second energy, it has 8 electrons. And then it's in the third row, and it has 1 electron there. This 1 electron is very easily given up, right? Very low ionization energy. So the sodium ion is very easy to form. It looks a lot like the neon atom, right? The one that preceded it on the periodic table. The sodium ion is a happy ion. Chemical bonds are essentially attractive forces holding atoms together in compounds. And they can be described as either molecular, that is delocalized, or atomic, localized orbitals. And there are 3 types of bonds, 2 of which we're going to cover more extensively. The first one is ionic bonds, and here you have the electrons are actually transferred between the atoms. So essentially those are electrostatic forces that bind them together. We'll talk about exactly what the shape and how these appear in nature. The other ones are covalent bonds. Here the electrons are shared. So that's the difference. Electrons transferred here, electrons shared here. These are typically between non-metallic elements, the right-hand side, that's what RHS means, of the periodic table. Metallic bonds, these are where you have all of those things in the transition metals and all of the things that we regard as metals, outside of the alkaline metals and the alkaline earth metals. This is the outer electrons move freely throughout the metal. You sort of have an electric gas within a rigid structure of the metal atoms. These conduct heat and electricity very well. So, first of all, ionic bonds. These are chemical bonds of electrostatic attraction, and what they do is they form crystalline solids in a very ordered geometric structure. Because of the nature of this course, we're not going to get into all the different variations of how those crystalline structures can be organized. But let's look at sodium chloride as an example. Here you've got the small sodium ion, because remember it's tight, it's lost that electron, it's very tightly packed. Then you have the chlorine atoms next to each one of them. Each one of them has many different pairs to each one. You can't say that a single sodium or a single chloride is bonded to a single one other atom. There's no single NaCl molecule in of itself. That's what per se means. So sodium loses an electron, chlorine gains an electron, thereby having these sorts of spatial differences between the two atoms. And here is a cubic structure of table salt. This is sodium chloride. And you can see that there's going to be a whole lot of different sodium and chloride atoms in here. And they all have pretty much the same type of shape. Okay? Of course, if you add water to it, it'll hydrate and you'll have a different shape. But basically, crystalline salts all will have a given shape based upon their size and makeup of the different atoms in that structure. So the energy in electrons and ionic bonding means that there's energy released when it is formed. Okay? The energy has to be given in so for sodium to give up that electron, and the chloride ion is formed with the release of energy. So overall, for this to form a salt, there has to be a net energy release when these two ions come together. So what they're doing here is they're looking at this in terms of half reactions. You could have just this Na going to Na plus, right? And at the same time, you could have Cl on this side of the equation going to the Cl minus. So this is the overall net equation, but each one of these is regarded as a half reaction. The electrons lost or gained to form the octets. The number gained has to equal the number lost. After all, it is an equation. So ionic compounds and formulas would look like this. If you've got calcium, notice that's in the second column, the alkaline earth table, and has two outer shell electrons. Fluorine has one vacancy in each one. Therefore, for these two to be given up, you need two of these molecules, two of these atoms, right? So the overall compound then is calcium fluoride, CaF2. The formulas list the elements of the compound and their proportions. The proportions have to do with the subscripts in them. The proportions are decided by the electron gain or loss. So for these ionic bonds, that means electrons are lost and electrons are gained. Most of these are white crystalline solids. I know, it's going to make, so next time you're stopped, it could be almost anything in that little baggie, right? They're white crystalline soluble solids in water. Families 1A and 2A lose electrons and form positive ions. Over on the right-hand side of the periodic tables, families 6A and 7A gain electrons and form negative ions. Okay, let's go on then to covalent bonds. These are chemical bonds formed by sharing pairs of electrons. Electrons shared to again form octets ideally. The overlap of shared electron clouds between the nuclei yields a net attraction. Atoms within covalent compounds are electrically neutral or nearly so. As you'll see, they have some sort of a dipole moment at times, but not always. So if you look at the compounds and their formulas, these are held by covalent bonds. You have a hydrogen ion here, and a hydrogen hydrogen atom here, and a hydrogen atom here. Each one of these is not satisfied. If they share those electrons, each one of their own, essentially you have two of them together. And when you are doing this for electron dot representation, 2 dots equals 1 bond. Okay? So for chlorine and chlorine to go together, you've got a 1 lone one here, 1 lone one here, and they become the shared ones right here, right? This is your bonding pair of electrons. So the lone pairs are not shared. These out here are the lone pairs. This right here is the lone electron. These are lone pairs. And so this is a Lewis type of structure where they're using dots in place of electrons. So whatever the octet rule is, you check where its position is in what group and put that many dots around it, usually in groups of 2, right? Because remember from the magnetic spin number, there's 1 up and 1 down in each of those orbitals. So you can also have multiple bonds. That's sharing more than 1 electron. For example, here you've got 4 electrons around each carbon, and you've got 4 hydrogen, each with a single electron as well. So what you can do is you can have an ethylene bond where you have 2 shared here and 4. So you've got 1 bond here, that's 2, 4, 6, 8 electrons around this carbon. Here you've got 2, 4, 6, 8 around this carbon. So both of these carbons are going to be satisfied. Hydrogen only needs to be 2 to be satisfied, right? So these 2 are shared here, these 2 are shared here, these 2 are shared here, and these 2 are shared here. So it's the 10 electrons form a double bond and 4 single bonds, right? You'll see also we have other ones where if you just have, in this case, where you've got 2 of them, you would have to have a triple bond here. Okay? So, let's go back and remember where we left off in the last chapter. We had for sodium, it has the neon structure plus 1 electron. Magnesium, neon structure plus 2 electrons. Aluminum, 2s plus that 1 in the p orbital. Silicon adding 1 to the p, 1 to the p, 1 to the p. And so you can see how it builds out. You've got sodium with 1 extra electron, magnesium with 2, aluminum with 3, silicon with 4, phosphorus with 5, sulfur with 6, and chlorine with 7, and then you get to the happy argon, right? You could do this in the prior table with lithium, right, beryllium, and then you'd go all the way over to boron and carbon, nitrogen, oxygen, fluorine, and in that case, neon. So here is an example where you've got sodium forming a sodium ion with 1 electron left over. Calcium forming a calcium ion with 2 electrons left over. Again, this is ionic. Then you have the chlorine ion formed here, sulfur ion formed here. Sodium chloride becomes sodium chloride here. Magnesium oxygen becomes magnesium oxide. Calcium atom becomes calcium fluoride. These last 3 were examples of the anions and cations using the Lewis dot type of structure. And we'll stop there and go on then to the next section.